Okay, Cup. Welcome to the second to last class. This will be our 7th out of 8 class. This is a summer pre-course, interactive mathematics with Mathematica. Again, it's meant to be a foundation course, prepare you for linear algebra and calculus proper, but at the same time, it's supposed to instill in you a sense of analytical thinking and the role of mathematics. And it should be a lot of insightful motivation as to why it is we are working with vector, why it is are we working with distinction between discrete or continuous number or countable set versus infinitely and uncountably infinite set and so forth. So all these are basically core element of mathematics, but they are chosen because they will be the foundation of all the analytical discipline later on, whether or not we're talking about analyzing data, creating probabilistic model, or doing data science, or even visualization, graphic visualization in the application. And of course, a lot of this is because it's done on mathematical computation platform, namely Mathematica. It allows you to prototype idea and function. And in fact, just to be clear, the reason that you are being equipped with Mathematica is not necessarily because it's the most powerful mathematical engine there is out there. Okay, that's not the main thrust of equipping you guys with Mathematica. The main thrust is that some of you will be working in technical area. Okay? So you will be working on sustainability challenges, healthcare solution, smart cities, and of course, some of you will be working with applied digital intelligence. So that's a lot of machine learning and data analytics and computation and so forth. But those of you who are working in a non-computational area, again, healthcare, sustainability challenges, smart city design, and so forth, green revolution, a lot of the innovation will have to be, for lack of a better word, has to be prototype. You can't really communicate your idea in pictures. Okay, you just can't just draw doodles. Like this is a dream app of how we would create a solution to solve the ecological or environmental challenges. You have to do some kind of prototyping, some kind of putting your idea down. But in the old days, you would put your ideas down to paper, right? And maybe in the 80s, you would put your idea down to PowerPoint. Well, now you have to put your ideas down to a prototype application. And because Mathematica has a very powerful, interactivity functionalities, it would allow you to mock up your idea into a mock application. But it's not just a user interface mock-up. It's not just, this is a screen, this is a button, this button would allow you to do this button will allow you to do that. No, because it's actually underneath all that, it's actually a computational engine. So the mock idea can be demonstrated computationally. And I have several examples of those. I use them in my consultation business even, say, well, this is the sort of portfolio optimization that you can do. Okay, adjusting this parameter, get this risk return profile, and so forth. And this is all done with interactive tools that I've been showing you sporadically with Manipulate and so forth, right? And so let's say once the client is down with the idea, so to speak, and you want to develop an application that perhaps interact with the database, in a very fast and efficient way, then you can commission a programmer to write the program in C, in JavaScript, in Python, in whatever language it is that is used for industrial implementation. Okay. So again, it's a prototyping of idea that I want to get across, and it's the idea that mathematics is an analytical language. Everything we do, everything that I teach you has significance. Okay. Why we work with variable, why we work with parameters, why variable comes in scalar form, in vector form, and in the future you have variable that comes in matrix and tensor form. Okay, these have all real correspondence with the physical system that you would like to model or optimize or create some kind of a functional application for. Okay, so now let's okay, let me share the screen, and as usual, this is your folder. So let's go to the Mathematica notebook. Now, this is the mind map thing. Let's see. Let's go to the Mathematica. Again, this is a work in progress. I'm writing an interactive textbook, and I in the earlier classes we did have a lot of example that are sorry, I have to open with earlier version because I haven't activated the newer version yet. This, by the way, is done mathematically. This is called mathematical function. Now, okay, so let's see. Let's also bring up the class outline. Okay, so roughly speaking, you see that in the beginning, it's the elemental thing, the very basic thing. It's basically about numbers. What do I mean by number? What can we do with number and so forth? What do numbers belong to? What do they represent? And then around here, okay, when we go into matrix algebra, okay, when we go to linear algebra, working with vectors, we are focusing on a special type of variable, which is not all that special. In other words, it's very general. Yeah, it's quite interesting. In normal language, in parlance, something special is something you like, right? You like something that's special. You don't like something general, like everybody has it. But in mathematics, something that's special means that it's only specific in application. So general is a lot more powerful. Yeah, think of Einstein's special relativity. Special relativity doesn't mean that it's so special, we give it the name special. It's special relativity because it only applies in what's called inertial frame of reference. Once you throw in gravity, then it doesn't work anymore. So for that, you need to go to general relativity, where you can incorporate acceleration, gravity, and so forth. So in mathematics and in analysis, in problem solving, general is better than special. Okay, so in this case, even though I said, well, it's a special kind of variable, it's the variable that represents a list, an ordered list of number. Okay, but because the application is so ubiquitous, you can visualize or you can represent just about everything that you are going to be working with analytically or analyzing with vector. Okay, a human being is a vector, right? Your client is a vector of features. Okay, vector of measurable features. A country is a vector, right? So every country has, say, socio-economic statistics, maybe to represent a good idea of what a country is like socio-economically. You have to represent it with an ordered list of, say, 20 or so numbers. Okay, GDP per capita, infant mortality, okay, unemployment, okay, maybe land space per capita, okay, amount of healthcare coverage, okay, age, okay? So median age, mean age of a population, or maybe some kind of distribution statistics. So all this number describes a country, right? So all this number, okay, say a country represented by a good representation is a vector of 20 socioeconomic numbers. Your client, again, is a vector of something. Okay? If your client is, if you're making a dress, you're making a suit, you tailor, okay, then your client is a vector of body measurement, right? The waistline, the inseam, the shoulder, the neck, whatever circumference, all this, okay? And so you work with vector a lot. You work with vector a lot. Now, without, well, I might as well just write something down. So,
Dr. Punjai, just sorry to interrupt you.
Yeah, no problem.
From my screen, all I can see is your folder at the moment.
Oh, okay.
I don't know if that's just my end or if it is.
Yeah, might be.
global.
So let me share again. Let me share. Okay, let me share the whole screen. Okay. All right. Can you see this now? Sorry. That should be better. Yeah.
That's better. Yeah.
Okay. So again, so this bunch here is about the basic elements, the number. Okay. What can you do with number in the most basic way of thinking? Okay. Multiplication, addition, comparison. Okay. Doing some kind of function on it. You know, making some kind of assignment, making some kind of decision. Is A bigger than B, or is A equal to B, and so forth. Yeah, some kind of logic. So that's the most elemental thing you can do. And then around here is when we focus on what I said, a special, but in fact very general type of variable called vector, yeah, which is an ordered list of number. Now, what can you do with it, right? So let me just write down in words. So remember what we have been doing. What we can do given a vector. Oops, sorry. Okay, given a vector, okay, say v, okay, v. What can you do with it, right? You can multiply it, a vector, by a scalar. That's just a number. That means that number, if it's 2, then you basically make everything twice as big. If that scalar number is -1, you just flip the sign of everything. Okay, you can't always do this in a meaningful way. For example, if your vector is a vector of measurement, okay, height, waist, and so forth, a negative height and negative waist side and negative weight doesn't mean anything. Okay, so mathematically you can do it, but it has no correspondence. On the other hand, if your vector is a coordinate, right, 3 kilometers east, 4 kilometers north, right? So it's northeast, right? 3 kilometers east, 3 kilometers north. Well, if you want to go back, exactly what you want to do, you want to do the same vector, but reverse. So you multiply everything by -1. You go west instead of east, 3 kilometers. Instead of going north, you go south, another 4 kilometers, and you get back to the same thing. So it's kind of reversal, right? So that you can do. And coordinate, you can reverse. Okay. Now, physical, like I said, physical measurement, you can't have negative, but you can certainly make it smaller, right? People do shrink. As they get older, their spine compressed, and you get an inch or two shorter when you are in your 80s, let's say. Okay, and you may lose weight. You can do that, but you can't go down to 0. Yeah. So you can do that. You can multiply a vector by scalar. What else can you do? You can add or subtract 2 vectors. Yeah, that's interesting, right? That's interesting. That's like what I said earlier, the notion of algebra. You add 2 vectors, and you still produce something else that is also a vector. Okay? So this is the notion of doing something and getting something that belongs to the same member. Okay? mentioned about the notion of species, right? You can get two monkeys, a monkey boy, monkey girl, get married, have baby monkey. That baby monkey will have the exact same genetic dimensionality as the parent. Yeah, the value will be different, but it would have the same genetic architecture, number of genes and so forth as the parent. Yeah. What else you can do? You can multiply, okay, a matrix to a vector. Yeah? And that is the notion of, what did I say? In a physical coordinate, it's like moving a point, right? But in a more general sense, we don't say we are moving a point. We actually transforming. Okay, so you're transforming. And this transformation is called linear transformation. Now, I did not go into details about what I mean by linear transformation. Well, a linear transformation, first of all, a transformation is just a function, right? Now, in this function, you multiply a vector by a matrix. That's an operation. That's a function. That's, you're doing something to it. Okay. The linear transformation is one of those things where if you get twice as big of an input, okay, whatever output you got, you get twice as big. So what all it means in this case, all you need to know is that a linear transformation, I'm going to write it in a general form. Okay. A linear transformation of something, x. Okay. It's linear because if you multiply x by some number, say 7x, is equal to 7 times linear transformation. That's exact. That's it. That's what you mean. That's what it means by linear transformation. It has a sense of proportionality. Okay, it keeps the sense of proportionality. Instead of x, you get something 7 times as big. Instead of getting L of x, you get 7 times something as big. So this proportionality goes through, promulgates through the transformation. Now, obviously, I'll give you a very good, simple example of things that don't have this property. Okay, let's say 7x, okay, to the power 2, right? Now, this is certainly equal to, okay, 49 x squared, right? Right? Now, my question is, well, if the linear transformation, so is this equal to 7 times linear transformation of x? Yeah, this function. The function is 2 raised to the power 2, right? Now, instead of having x, I have 7x and I raised to the power 2. Does that end up being 7 times as big? No, it's not. It's actually 49 times as big. So obviously, this is not linear. Okay. So this is basically it. Now, this is. It sounds like matrix algebra. Matrix multiply by a vector. Multiply by a vector produces another vector, which is a linear transformation of the original vector. And I gave you an example of like a weight loss matrix, something like that, right? So you have certain weights, certain waistline, and you go through this diet, whatever, or exercise routine, and you come back, you're a little bit lighter, and maybe your waist size is the same, or maybe even less, and so forth. So that sort of thing, but it has that kind of proportionality. Okay, so the same weight loss program, if you apply it to the person who is 10%, okay, the person who's 10% heavier and 10% wider at the waist, it would still achieve the same transformation, but the result we'll still have that multiplication factor of 10%, right? So a big person would maybe go through the weight loss matrix and it gets a bit smaller. Someone who's 10% bigger will also get smaller, but at the end of the day, it's still 10% bigger than the first person. It's that kind of linearity. That's what we mean by linear transformation. Okay, and I this morning I just made up this example just to show you a little bit about the second notion. So the first notion is that you can use this to represent transformation. Okay, and second thing is you can represent what? What else can you do with vector? That is very important. You can use it to represent when you say that matrix multiply by I'll call it left hand side vector equal to right hand side vector. Same thing, right? Matrix multiplied by a vector produces another vector. Matrix multiply by a left hand side vector gives you the right hand side vector, except the use is different. You don't think of it as transformation. You think of it as what? Represent a system of equation, right? And so if somehow instead of having a matrix multiplied by the left hand side vector equal to right hand side vector, you say left hand side vector is a solution to that system of equation. And how do you find that? How do you find that? How do you find that? Well, left hand side is equal to matrix. You find the inverse times matrix times left hand side equal to matrix inverse and then right hand side. All right. So originally you have let me write in a sort of more mathematical notation. A, okay, x equal to y. Okay. Now you want x, right? What you like to do is find x. So what you want to do is x is equal to y divided by a. Okay, that's intuitively what you like to do. But you can't do this because you can't divide a vector by a matrix. You can only multiply. Okay, that's the name of the game. That's the mental exercise I took you through the beginning of last class. Imagine you want to divide, but you're not allowed to use the word divide. So what do? You multiply by something that multiplies and neutralize the effect. Okay? So what you do is x is equal to a, something that's inverse. So I'm going to write this notation a minus 1. Okay? X is equal to what? X is equal to a minus 1. Why? Because when you write this again, you're given this, so you find a inverse somehow. Yeah, and how is the subject of your linear algebra class. Okay, so I'm telling you what you want to do. I haven't shown you how to do yet. I'll show you how to do in a simple case. Find this so that when you do this, take the original equation and you multiply by this thing that undo, right? So this is like exactly what we were talking about, sort of like reversing, right? You were moving somewhere and you're going back to your origin. So you multiply this to the left hand side and you multiply this to the right hand side. Well, it turned out that this thing gets canceled, right? This thing gets canceled, and I'll tell you the notion of canceling a little bit later. Okay, and so this thing basically goes away and you get your solution. And that's how you want to do it. Okay, that's how you want to solve. Now, likewise, just as something in algebra, in high school algebra, you have something where ax is equal to b. You can do this if a is not equal to 0. Okay. In this case, the difference is you have something else called, you can do this as long as A inverse exists. And it only exists if this thing called determinant, which I haven't told you how to do it, not 0. Okay. So in the case of, 7x is equal to 92, okay, because 7 is not 0, you can take it to the other side and divide it. But if A is 0, you can't do it. Instead of checking whether or not A is 0, you're checking this property called determinant is not 0. Okay. Now, what is that determinant? Well, you find that out in the linear algebra class. Okay. But again, in the spirit of helping out Chris a little bit, I'll show you how it's kind of done in a small dimension. Okay? And that's also another philosophy or another approach of mine, which is to teach complex concept in lower dimension, in dimension that people can visualize. Okay, so can you guys see this? Oops. It's uploading to kind of. Where do I want to go? Okay, I want to go to here. Good. So let's set up the character. Now, again, I want to do this in a low dimension, as low as possible. So I have AX is equal to Y. My A is a 2 by 2 matrix of 4 value, A, B, C, D. Okay. What does it look like? Let's do this. Again, mathematical notebook, you will see this as a why do I keep doing this? That's weird. Okay, for some reason, I think I tend to accidentally set off some kind of calculation. Okay, open with, so maybe I was using the wrong version again. Yeah, on this machine, I have 2 versions. One version is activated, the other version is not activated. I think I have. So wait, hang on a second. So meanwhile, let me just review that. Okay. So we talk about this summation variable, blah blah blah, dot product. Okay, we did that 2 classes ago. Matrix representation, a system of linear equation, and that's what we want to talk about. And oh yeah, I might as well go over that concept that I mentioned last time, that in life, right? In life, if you have AX is equal to B, right? If A is not equal to 0, you get a unique solution. If A is equal to 0, you have 2 situations. Either the right-hand side is also 0, in which case anything would do. Any 0 multiplied by any number multiplied by 0 will get you a 0. So it has infinitely many solutions. The other situation is 0x is equal to 5. It's impossible. You can't multiply 0 by any number and get 5. So there's no solution. So in life, there are actually 3 possible scenarios. Unique solution, infinitely many solution, and no solution. Okay? Unique, infeasible. Infeasible means no solution. And infinite solution means indeterminate. Okay? So these words are used interchangeably. Now, the unique solution corresponds to a very nice situation you have in high school, in grade school, right? The second and the third situation is the sort of like situation where the left-hand side is equal to 0. Okay, so sometimes instead of saying situation 1, 2, and 3, I would say situation 1, situation 2A, and situation 2B. I also went on to say that even though in school you would get unique solution, and sometimes some high school or some grade school will also teach you situation where you have infinitely many solutions, but you will never get a problem that has no solution. Well, in real life, things are a little bit more complicated. You would actually, I can tell you this, in my professional life, I almost never run into a situation where my problem has one unique solution. Almost never. Okay? It's always either no solution, in which case something has to be fixed to make it feasible. Some kind of engineering, reconfiguration, some kind of reformulation, rethinking, allowing more flexibility. That's life, right? When you have no way out, infeasible, you have to find a way out. So that's more like an engineering problem, finding the solution where it doesn't exist. Okay, so the solution is not there. You have to make the solution possible. But that's one situation. The other situation is the situation that you most often encounter in business. That is, you have infinitely or you have multiplicity of solutions, and your job as an analyst, as a business owner, as a CEO, as a decision maker is to narrow down from the set of multiple solutions the one that best achieves your objective. And that situation is called optimization or optimizable problem. And that turns out, to be honest with you, the most common type you will find in life. Okay, so it's really funny that infinitely many solutions is in fact the norm of your professional life. Okay? It's the norm of your professional life. Okay. Right. Okay. So this I want to show you real quick. This is the let me make it a little bit bigger. Okay, this is my A matrix. Okay, let's look at matrix form. Just looks like that, right? Okay. So if so what about X? Okay. Matrix from X, matrix from A, right? So basically, I put Y as well. Okay. So this is my system of equation. Let me do this. 1, 2. Okay. So this is my system of equation. Y1 and Y2 is equal to, let me minimize this. Y1, Y2 is equal to matrix A dot X, right? Now, because I have already done the multiplication here, the real Y is actually 1 plus X1, 1 times X1 plus 2 times X2, and then 3 times X1 plus 4 times X2. So let's see what that Y looks like. 1 times X1 plus 2 times X2 and 3 times X1 plus 4 times X2. So this is the dot product one at a time. Okay, so that's it. So that represents your system of equation. The problem that you want to do is do this. You want to somehow find this thing. You want to find this, but you don't know what it is. So you have to find something like this. Find, okay, find this so that you can do this. Okay, and because this thing cancel each other out, this is your solution. This is your solution. Okay. Now, let me just show you mechanically how it's done, first of all. Okay. So you have, so what you do is, well, you have y, right? Basically, you have to do inverse of a dot y. That's your x. Okay. And see if that gets you back. Okay. Oops. Inverse of a. Yeah. To simplify. Okay. This is by design. Mathematica will multiply everything out and keep everything in the sort of like, you know, some kind of default form. So sometimes you want to expand, sometimes you want to simplify, but that's it. That's your solution. Okay. So let's say I want to set the right hand side to something like, okay, is equal to, okay, ax. Now I'm gonna set it equal to something like 5 and 6. Okay, 5 and 6. So what you have now is what? Is 1, 2, 3, 4 times x1, x2 is equal to y1, y2, which is 5 and 6. And you want to find the inverse such that when you multiply this to the right hand side, again, you are dividing, but you can't use the word divide. So you have to multiply by the inverse. And this thing goes away, and that's your solution. And that's your solution. The trick is exactly how do you find that? Well, let me just show you, okay? Let me just show you what it looks like. Let me go back to original form, okay? Let me clear everything. Let me clear the value and I start over. Okay, now I'm not gonna give a number, so I'm just gonna do this. Okay, so everything is gonna be in symbol. Okay, let's do this. Okay, now let's see what it looks like. Matrix form A. Right now, I want to see what matrix form of A inverse is. Of inverse of A. Okay. See, this is a matrix form of the inverse of A. I guarantee you that if you do this, now you can multiply matrix and matrix, right? Do this as an example, as a homework, if you like. You multiply this by hand. What are you going to get? What are you going to get over here? Well, notice this is A, D, forget the bottom. You notice the bottom is exactly the same for everyone. Okay? A, D minus BC. AD minus BC. Okay? The whole thing divided by AD minus BC. Oh, wait a minute. So that's 1. Same thing here. Minus BC plus AD. This is going to get you 1. What about this? D times A minus D times B minus D times B. This is going to get you 0. So remember the concept and multiplicative inverse of something, of Q. is something that multiply to Q and produces multiplicative identity, right? So this is the matrix. This is the inverse. It's inverse because when you multiply it, you get this. And this is the identity matrix because you can multiply this to anything and it does nothing. It does nothing. Okay, you can multiply this by y and z. You're gonna get y and z. You multiply this by q and r. You're gonna get q and r. It does nothing because it's a multiplicative identity. So this is exactly how you solve the problem. Okay, so this is your A inverse. Now notice, remember when in grade school, AX is equal to B, you cannot do this if A is equal to 0. Well, in this case, the matrix is your multiplier. You cannot do it if this thing is equal to 0, because this thing will always be at the bottom. This thing determines whether or not this matrix collapses, basically. Okay, you can't do the inverse. So this one determines whether or not you can find the inverse. If this is 0, all bets are off. You're done. And that's why this thing is called the determinant. And that's why if you write in the function, this is a built-in function, determinant, it's DET because it's a shorthand. Used so often, they use shorthand. DET of A is equal to minus BC of AD. So it's AD minus BC. Now, finally, let me give you an intuition why this is the determinant. This is the determinant because you remember the reason the problem you have with to begin with is that you have two equations into unknown, right? So the left-hand side has to give you different kind of slope, right? You have to have a line that that does this. Okay? You have to have a line that does this, right? What you don't want is this. Oops, sorry. Another line that has the same slope. Now, the reason you have the same slope is because A and B and C and D are in the same ratio, right? So you have the same slope, okay? This one is no good if the left-hand side creates two lines with same slope. Okay, this is no good. Let me write this again. It's no good if the left-hand side, I see A, B, C, D, if A, B, C, and D, okay, creates two lines with the same slope. Well, it's the same slope if A equal divided by B is equal to C divided by D, right? So let's make it the same thing as A times C equal to B times D, right? Or A minus BD is equal to 0. This is your determinant. Okay. So basically, all AD minus BC, sorry. sorry, okay. All that AD minus BC do is check whether or not the ratio are the same. Now, obviously, this is kind of easy, right? This is kind of easy. Now, so determinant of this guy is easy. Yeah, it's easy, right? The difficult thing is, of course, when you don't have a 2 by 2 matrix. Now, let me just show you, I kind of wrote down here another example. So this is my new A. This is just 3 by 3 matrix, right? Okay. Just this. Guess how complicated that is. Let's look at matrix form of inverse. Okay. So that's why you would lose the intuition in general term. That's what it looks like. And anybody wants to guess what the quantity below here is? Well, the quantity here cannot be 0. So you guessed it. This is the determinant. Okay. So this term here cannot be 0 because it's in the bottom of everything else here. Okay, in all this. Okay. So again, I want you to have the intuition in 2D, right? If it has the same slope, it's problem. It either has no solution, or if it lies on top of each other, it has infinitely many solutions. Okay. Okay. So let me in life you have 3 situations, 2 equation, 2 unknown. You get a unique solution. Okay. This is the most common situation in school. This is the least common situation in life, because if there's only one solution, you are not paid to do any analysis. Okay, you shouldn't earn any money to make a decision because the decision is made for you. Okay, you are contracted to make 500, I don't know, gift box, and you can only make 500 gift box. Okay, you are asked to make 50 cups of coffee, and you only have enough coffee to make 50 cups, right? Yeah, you can do the execution job. You cannot do the management job. You can't do any decision making. You can't do any planning because you have 50 cups of coffee to meet 50 cups of demand. That's your unique solution. Now, the second situation is when you have 2 equations and 2 unknown. Unfortunately, you only have 1 equation. One is just on top of another. Okay. Another situation is you have 2 equations and 2 unknown, but they are parallel. This one is an engineering. Okay. Or if you want to be hopeful about it, it's where your innovation comes in. Okay. Innovation means you have something that's not doable before and you make it doable. But you can also do innovation here. And this is a business problem. You have infinitely many solutions. The question is, which one is closest to here? Say, this is your dream state. Okay? This is your solution. This is your dream state. Which one is closest? And that is called optimization. Okay? Now, this is going to be my segue into calculus, believe it or not. Okay? This is my segue into calculus. Okay. Let me just focus on this. Okay, once again, I'm going to say this one more time. This is what you see all the time in school. Sometimes you see this, you never see that. In life, you rarely ever see this. You see those 2. This one you have to either innovate or engineer your way around, so that eventually maybe you adjust a little bit and you find a solution. Okay. But most of the time, and this is where optimization comes in. You have infinitely many solutions, or you have multiple solutions, and you have to choose the one that best gets you where you want to be or closest to your objective. So this is your happy point place. Or alternatively, this is your unhappy place, you want to be away from. So let me draw this picture instead. And this is your happy place. Okay? This is your happy place. Let's say you're over here. Let's say you're over here. You can be anywhere, right? How far are you? That's far. How about here? This 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 far. Well, you get the point, right? You get the point, right? So if I tilt this picture a little bit, if I tilt this picture, okay, and let's say I call this 0, and this is my distance in kilometer along this Sukhumvit Road, okay, which kilometer would get you the closest view to this building that you like to see so much? It's a nice view. It's a nice building, okay? So think of it as, well, maybe it's a country road, okay? It's a country road. There's a nice tree. You want to go take picture, selfie picture, right? And you can get a ride here. Ask your bride to drop you off anywhere. Where would you like him or her to drop you off? Obviously here, right? Right? Obviously here. You don't want him or her to drop you off here because this is the distance you have to walk. You want to be dropped here because this is the shorter distance. So instead of looking at this, I'm going to plot the distance along this axis. Distance to happiness. Okay. Now remember this picture because I'm going to redraw this graph. It's going to look like this. Okay. And the distance will kind of like closest will go away. It would look like this. And here is where the distance is closest. Okay. So keep this picture in mind. Okay. Keep this picture in mind. Distance to happiness. Okay. And this is some beginning. Okay. So you can be anywhere. You can be dropped off anywhere. But the distance to happiness is closest here. Okay. So keep this picture in mind. This has two elements. First of all, it has that element of infinitely many solutions. You can be anywhere. You have another function which maps your location to this. So this is your objective. Function. It's a function of what? It's a function of location, right? In other words, your location is your, anybody? Man, I should give bonus point for this, but there's no point in there's no point in this class. So the location is your decision variable. Okay. Now, remember, variable is something that can change. It can change like time. It's a variable, but it's a deterministic variable. It moves along at the rate of 1 hour per hour or 10 seconds per 10 seconds. This is a different kind of variable. It's the variable that you, not nature, not dynamics, not law of physics, but you can decide. Okay, so before you decide, it is a variable because it can take on any value. The person can drop you off here, 1 kilometer, 2 kilometer, 3 kilometer, 4 kilometer, 5, 6, 7, 8, 9, 10, whatever. It's a variable. The location along the road, let's say this is a country road, is a variable. You can decide. If you decide unwisely, you decide here. That's not wise. You decide here. That's not wise. If you decide here, you are wise because it takes you the shorter amount of walking to your happy point. Remember, this function here is not a terrain. This does not represent the map. It represents how close you are to the happy place as a function of location. So this location is your decision variable. Okay? In this case, your objective function is something, do you want to maximize it or minimize it? You want to minimize it. Okay, so let's go back to here. Okay? Actually, I'm just going to start a new. Okay? Let's say f of x. Okay, I'm just making it x minus 5 to the power 2 to the power 3. Let's see, power 2. Okay. Log of x plus. Okay, I'm just making some kind of funny function. Okay. And I'm going to ask, okay, we want to minimize f of x for x. Okay. Oh, I forgot to clear x. Sorry. I keep using the same symbol. Okay. Ah, this one's no good. This one no good. Well, let me do this. Okay. This one happened. It did find the minimum. The minimum is x go to 0. Yeah. Okay. This is some kind of weird function. This is some weird function that I just came up with. Okay. Now let's see what this function looks like. Plot f of x. Okay. X between minus 100 and 100, I guess. Okay. Minus 100. That's not fun. Okay. I'm just making really funny function. Now, let me do this first, just to make it simple. Okay. Okay. So this is what the function looks like. The function looks like. Okay. And this function here Okay. Oops. Yeah, I'm just making some function up. You know what? I'm making life too hard for myself. I'm just gonna make it like this. Okay. Okay. So this is some function. Okay. And this is your location on that street. And now location has arbitrary 0. You can go here, go there. The point that here is your decision variable. You can be anywhere you like. Okay. Now this is the distance to your happiness. Okay. This happens to be the distance function. I asked the computer to say minimize this distance to happiness for any value of x. So find me the location that minimizes this. So the location is 5. At 5, this is smallest. And the distance is 78. And it's obvious because when the x is equal to 5, this thing goes away. And you're left with 78. Okay. The idea here is you can do it in many dimensions. You can do it in 2 dimensions. Okay. So let's say you have 2 dimensions, x and y. Okay. Okay. Now minimize f of x and y for x and y. Oh, I forgot to clear y again. Okay. Okay. This one, it gives you x is equal to 5, y is equal to 5. Oh, that's obvious, isn't it? It's kind of symmetric. So let's make it 8. Okay. So that's it. Now I can also plot down. Now I need to plot 3D, right? F of x and y, x minus 5 to 10, then minus 5. Okay. So this function here, right? Instead of saying where should you go on this road, it's where should you be on a 2-dimensional coordinate so that the distance to happiness is smallest. Okay. In this case, what? In this case, well, let me make it a little bit. It's not gonna do much, but okay. So it gives a little bit more sharp, but somewhere here, okay, somewhere here, what sort of like there's a minimum point. Idea here is you want to find that point. This point should be around here somewhere. Okay. So this is the concept that you want to find something that's minimum. Okay. Now let me go back to plot x to the power 2, x to the minus 5. Okay. Right. Now notice. Okay. Let's say this is the location. This is a decision variable. You want to minimize. Okay. Now let's draw another one. Let's say you want it's something like happiness. Instead of distance to happiness, it's a happiness function. Okay. Now, where do you want to be? You want to be here. Okay. Where you want to be? Okay. So you want to be here to get there. You want to be here to get there. What is the common point? between these two pictures. They're obviously different picture, right? One goes up, one goes down. But what is the common theme here? The best solution happens when the graph is neither decreasing nor decreasing, right? It's kind of flat. Think of it. At the bottom of the bowl, it's flat. At the top of the hill, it's flat. The bottom of the bowl is flat, meaning over here, you go down, you go up. Now, this is not a physical terrain, right? This is not a physical hill, but you can think of an imaginary traveler traveling in the space of function. It's kind of mathematics space, right? So instead of having a location of where you are, okay, this is you. You can travel here, right? This is your decision variable. You can decide to be dropped off here and there. This point is closest to your happy point. Now imagine that there's an abstract, you know, sort of like an abstract being that actually travels along this line. You can see that this being travels along the line of your objective function, and it's going down, 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 down. It's going up, 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 down, 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 up, 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 up. Right? In other words, by going from here to here, you are getting closer to your happy place. By going to here, from here to here, you get even closer. From here to here, you even closer. But from here to here, you get further, get further, get further, get further. So this imaginary being is decreasing the distance to happiness, go down the distance, and then increase the distance to happiness. Gets closer, gets closer, gets closer, get further apart. So you can imagine that there is some kind of improvement or worsening. This is improving, 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 worsening, 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 worsening. Now, instead of looking at the top picture, let's look at the bottom picture. Let's say this actually represents happiness, not the distance to happiness. This is actually the happiness score. If you're over here, you're not that happy. If you're over here, you are very happy. And this is represented by a sort of like abstract ant that crawl along this line. It's getting closer and closer, improving, 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 getting worse, getting worse, getting worse, getting worse, getting worse. So if you go back this way, better, 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 worse, 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 worse. So you can imagine that from this ant perspective, every time he goes to the right, he can either improve or worsen. And how do you quantify that? How do you quantify that he gets better or he gets worse? Obviously, slope, right? If the slope is positive, then you are getting better. If the slope is negative, you're getting worse. If the slope is 0, okay, and you have been getting better, and if you kept going, you'd be getting worse. You're actually the best place you should be. Same thing with the other picture. Go back to the original picture, right? This is the minimum distance to happiness. Okay, so this is too far. So you want to decrease this. So you get negative slope. Because every time you move to the right, the distance gets shorter. That's what negative slope means. As you move, it gets less. That's what negative slope means. As you move to the right, it gets less and less. So you shorten the distance, shorten the distance, shorten the distance until you get the minimum distance to your happy point. If you kept further to the right, what happened? You keep worsening, 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 right? Because you get further apart. So you can see that from the negative slope to the positive slope, there's a point where you actually have no slope. Okay. Now, depending on whether or not you want to be minimizing or maximizing, okay, the transition is different. You go from negative slope to positive slope, or you go from positive slope to the negative slope. But at that particular point, it's the same story. You are standing on flat land, not you, the abstract ant. The abstract ant is crawling on a flat land. Okay? There's no slope. So this is the notion of a slope. Now, there's also another notion of slope, right? This is a notion of a slope. What's the difference between the picture I drew here and the picture that I just drew before? This is a constant slope. Okay, this is a constant slope. Now, if you're going to measure the slope, okay, in this case, the slope is 3. By the way, I don't know if you ride a bicycle, but the gradient is how far you go up for every distance you go across. So if you're going horizontally 1 kilometer, and by doing so, you're climbing up 100 meters. Okay, that's a 1 in 10 gradient or 10% gradient. That's a very difficult bicycle track already. Okay. To the France, I think sometimes have 15 gradient, 25 occasionally at some spot. Okay, but that's it. That's the notion of slope. The difference here is that if you have a constant slope, does it matter if you take this distance divided by that distance, or this distance divided by that distance? It doesn't matter, right? Right? So whether or not you go 1 kilometer and up 100 meters, or you go across 500 meters and go up 50, it's the same slope. It's the same slope, right? It's the same slope. It's a constant slope. The point of something just now, okay, let's focus from here, okay, is that the slope is not constant. If you take the difference here, you get one line. Okay, so let's do this. Okay, so you have a hill. Okay, so this is very sharp. This is flat. This is downhill. This is uphill. This is flat. This is uphill. And let's say this is flat. So if you go do this and you do this, you actually measure a different slope, right? Now, obviously, if you did this and you're down here, okay, your average slope is this much. Okay, your average slope is from here is this much. Okay, but actually that doesn't tell you the story, right? Okay, because actually you went a steep hill and then you go down. It's not that you go up a gentle hill. Okay? So it's a very different story. Now, how can I make this more precise? What I want to do is the notion of rate of change. Rate of change. So now I'm going to be abstract. It is f of x. So instead of having a constant, I have this. Okay, I have this. Now, let me tell you right away, the reason you need this is because your function is not linear. Let that sink in. I just spent the last 2-3 lectures telling you the virtue of linear transformation. Now I'm going to tell you that linearity is useless because, you know, in real life, you don't have a constant slope. Well, in reality, those are the two fundamental tools you have in life. Okay? So let me write that down in Word. Okay? So this is the cornerstone of what you will learn in your first year mathematics. Linear algebra and calculus. Linear algebra allows you to study linear transformation on vectors. And remember that vector represent everything. Okay,นะครับ. Calculus allows you to study rate of change when the change is not linear. Okay. Rate of change. Okay. Ultimately, you will have in real life multivariate calculus. It's a little bit like calculus, but applied for list of variable. Okay, vector is like a list of variable, right? Yeah, x1, x2, x3. So you are going to learn this thing only on scalar x. So these are the two cornerstones, but in life, you will eventually come to the point where you will need to use them together or at different points in your problem. So this thing allows you to study vector. Vector is a bunch of numbers strung together to represent a multi-dimensional description of something. And it's very powerful. And the linear algebra allows you to study linear transformation of that. Okay. Calculus will allow you to deal with not vector, okay, not vector, but just scalar, f of x, okay? But you will be able to study a nonlinear transformation. So that's calculus, let's say 1. Okay, calculus 1 or something like that. And then in calculus 2, actually, that's not 2. This is calculus 0.5. Calculus 1 will allow you to do calculus on vector. Okay, on vector. Okay, except technically you won't be doing it on vector, you're just doing it on x1 and x2 and x3, okay, separately. Okay, so multivariate. Okay, something like that. So those two will allow you to basically cover most of the analytical problem in life. Believe it or not, if you can handle vectors, meaning you can handle object with multiple attributes, you can study their rate of change. By the way, converse of the rate of change is the cumulative amount of change. Converse concept. Right? And this is all calculus. Okay. So let me write down calculus. So, okay. Calculus. We're not going to teach you calculus. I can't teach you calculus yet, right? Because that's really your year 1 mathematics foundation. This is to get you to calculus, but I want you to have the anticipation. Calculus studies two things. Okay? Rate of change of, let's say, I'll just say x, as specified by f of x, where f does not need to be linear, right? In other words, f of 7x is not necessarily equal to 7 of f of x. That's it. That's what it means. Okay, so it's more general. So you study two things. You study rate of change. Okay, but okay, instead of rate of change, like on average, okay, you want rate of change exactly where you are, just very precise, very precise slope. And the word for it is instantaneous. Okay, this is actually not that difficult of a concept, right? Because you guys know how to drive. Well, you have been riding cars. Okay, if I say that it takes you 2 hours to go to Hua Hin, and Hua Hin is 180 kilometers away. Okay, an average rate of change. Okay, rate of change, rate. Okay. Okay. Change in position as a function of time. Okay, that's what your traveling is, right? When you travel, you change in position as a function of time. If Hua Hin is 180 kilometers and it took you 2 hours, okay, the rate of change is an average change. Okay, otherwise known as speed is 90 kilo per hour. Okay, that is it. Now let's just say that you have a function. This is where you are and this is time. So let me draw this again. But instead of x, I call this time. Instead of f of x, I call distance time. Okay, and this is kilometers. Let's say you start at 10 kilometers from Sanam Luang. Okay, and this is 180. Sorry. Let me make it simple. Let me just have you start at 0. Okay, so dt, and this is 180. This is 1 hour. This is 2 hours. Your average is this distance. 180 divided by 2 is equal to 9. But sometimes you go really fast and you go slow. In fact, let me draw another picture. You go fast, you go slow, you go fast. You actually stop for toilet break. In which case you don't make any progress at all. This is actually 0. Okay, so even though your average is the same thing as doing this, a constant 90 kilometers per hour, that's not your instantaneous speed, because right now your instantaneous speed between the first hour and a little bit, you actually stop at the gas station. So you're actually making no progress. Your rate of change or your speed is 0. So your instantaneous speed, where do you get that information? You get that information from your speedometer. It goes up and down. But if I plot your progress like this, how do I get the speedometer reading? It's the same thing as measuring instantaneous slope. Instantaneous slope. Okay, instantaneous slope. Now, so do you see what this is, right? Now I'm going to go to a particular function. Okay. So y, sorry. This is your speed, okay? This is f of x. X to the power 2. Okay? X yeah. Now, so obviously if I write f of a, I get a squared. So this is my function. This is my function. Okay? So let's plot f of x. Okay? X from 0 to 10. Now, let's say at this point, let's pick a point here. Let's pick x is equal to 6. Okay, at x is equal to 6. What is the slope? Anybody? Well, how about this? How about this? The slope is equal to the same slope the tangent line. Think of it this way. You have a slope. And then you have a ruler. So at this point, the ruler and the curvy line has the same slope. I'm drawing terribly. Okay? There, that's better. Okay? At this point, okay, actually, I might as well do that. So, how can I do this? Oops, sorry. No? How do I make curvy line? Anyway, okay, never mind. Let me go back to my terrible curvy line. But at least I have a good straight line. Okay. Now imagine this is what I want to do. This is what I want to do, right? I want to measure the slope. How do I measure the slope? Well, obviously slope is this distance divided by that distance, right? Right? Now, this distance is definitely not the same thing as from here to here. Okay? But as I make this smaller and smaller, right? I can do the same thing, right? It's the same ratio. It's the same ratio. No matter how big, it is the same ratio. Okay? It's the same ratio. So what I want to do is, if I make a zoom picture, really large. Okay? And I'm pretending here, okay? I'm pretending. Let's say I'm making a zoom picture, and that zoom picture is going to, this thing keeps blocking my thing. Okay? You can see that even though the original line is curved, over this small range, it's acting like a straight line. It's acting almost like a straight line. Okay? So I'm going to pretend that at a very small enough, I can do an approximation, right? Instead of finding another ruler and touch it, I'm just gonna forget it. I'm just gonna look at the line, okay? But I'm gonna take a very small difference. So take the height difference, divide by the width difference, but very small area. So this value, I want to say, let's say at x is equal to 6. Okay, say at x, I'm going to call it x naught, x0. Is equal to 6. Okay, it's equal to 6. Now, what I want to do is basically f of x naught okay, right? So this is x naught. This is f of x naught. Now I want to move it just a little bit, just a hair. Okay, and I subtract it by this. Okay, and divide. Okay, f of x divided by okay. Let's see, what do I get? I get the value 12 something. Okay, you see what I did there? This is f at x, this point here. This is f at x moving x by a hair. Divide by the difference. Well, obviously it's the same thing as this, right? Okay. That, okay, if you draw a line, a straight line from here to here, okay. In fact, let me plot something called okay. Now, this line has exactly the same slope as that line. Okay, it's almost touching at this point. It's almost touching. Okay, so you can see that again, this is you're traveling to Hua Hin, right? Except you're accelerating all the you stop. Now, to find the speedometer instantaneous speed, I take the distance traveled divided by the times it takes. But I would approximate it. It's the same thing as using a straight line, touch it at that point, and then measure the slope. Okay, except I don't want to do that. I want to just look at the original line. So I don't care about this line now. I'm going to look at just the original line at that point. Okay, and that point here has a slope, the rise of about 12 or 12 kilometers an hour, if that were the speed. Okay, so the instantaneous speed here is 12. It's close to 12. So instead of looking at the speedometer, I look at the distance you are at, say, 6 minutes, and compare it with the distance you are at 6 minutes and 1/10,000 of a minute, like a microsecond or something like that. Okay, so allow the time to move a little bit, the distance to move a little bit, and you divide the distance by time. You get the speed, except you make the divisor, the amount of time that lapsed, smaller and smaller. Now, it's not as high. To make it more, I should do this. Okay, and you get something that's very close to 12. Okay, the exact value is 12, by the way. Okay, if you do this. Now, technically, this is what I want to do. I have some f of x. Okay, I have some f of x. I don't know what it is. Well, I don't know what it is. Sorry. Now, at x is equal to 6, I want to find the change or the slope of that function. So I'm going to designate this as in the limit limit. There's a word called limit here somewhere. Limit. Okay, let me find the notation for it. Limit. Here. Limit. Okay. Limit of this. Now, instead of this thing, I'm going to represent it by a hair. A hair is like a small movement. A small movement is a change. In mathematics, they use this symbol, delta. Okay, it's a Greek letter, Greek, alpha, beta, delta. Okay, but I'm going to use capital delta. It's easy to see, capital delta. It's a Greek letter. Okay, for D, it's capital D. Divide by this as this goes to 0. 12. Okay, this is exactly what you want to do. Okay, I want to take the difference in height of 2 points as you move just a hair, and that make that thing go to 0. So normally this thing cannot go to, you cannot have 0 to the bottom, right? Well, this is what calculus exactly does. Okay, it allows this thing to approach 0 because the top also approaches 0. Think about it. As this thing goes to 0, this thing goes to 0. This thing also goes to 0. So it's more like 0 divided by 0. Except how fast is the top going to 0? How fast is the bottom going to 0? In fact, the ratio that it's going to 0 is the same. It's always 12. The top is always 12 as big as the bottom. Yeah. Well, it's not always. It's at that point. Sorry. Okay. So at that point, the ratio of this thing that goes to 0, this thing goes to 0, this thing also goes to 0. But at just about before it gets to 0, okay, the ratio is 12. And that's what you get. Now, let's say at some other point, x is equal to 7. It's 14. Notice any pattern here? It's always twice, right? So because of this way, because of the way you're driving, at 6 minutes, the rate of change is 12. At 8 minutes, the rate of change is 16. Okay, so at 10 minutes, the rate of change is 20 kilometers an hour, or whatever it is, kilometers a minute or meter per second. Okay, why is that? It just happened to be because this is how you define the function. So let's do this. Let's not put a value to it. Let's not put a value to it and find the general expression. Oops. For some reason. Okay. So notice that just as we observe a pattern, wherever you are, 6, the slope is 12. 8, the slope is 16. Because this is it, the slope. Slope is defined as this. And this, because it deals with the difference, this is called differential calculus. So this differential calculus is the study of this formula. That's it. It's a study of this formula. Okay, it's a study of that formula. It's telling you the rate of change as it gets smaller and smaller and smaller. Now, as it gets rate, I told you before that, where's the text here? The calculus studies two things, right? Calculus studies instant rate of change, and that's the formula we saw before just now. Okay, and conversely, if I gave you a log of how fast you are going, the flip side, the converse of this. Okay, so instant rate of change is sort of like finding speedometer reading from distance plot or distant record. So what's the converse of it? Converse of it is that what if you have speed record? Okay, you have this, you have speed record. You want to find cumulative distance travel from speed record. Okay. So calculus studies two things. One, instantaneous rate of change of x as specified by f of x, where f does not need to be linear. I'm just going to put it. Okay. E.g., for example, finding speedometer reading from distance record over time. Conversely, you study the converse. Conversely, you study the cumulative amount of change. I just say cumulative change, okay, of x as specified by the slope of f of x. Okay, slope of f of x. Okay, find the cumulative distance traveled from speed record. Because you have two things that are the flip side of one another. Okay, let me draw you final picture and we should be done for today. If I have two graphs, okay, and this is my distance graph, okay, this is my time, okay, this is my time. I want to find the speed, but if I have a speed, okay, if I have a speed, okay, yeah, remember this thing goes to zero, right? So you start at zero, you accelerate. So this is kind of a realistic way of travel, right? At time zero, you can't travel anywhere because you have no speed, right? Where's my mouse? Okay, so you accelerate, so you get fast, then you slow down, you stop. So it's like your speed goes up and then you stop. Okay, so this is your speed. The idea here is that from here, you want to find the rate of change. Okay, we want to find that. Okay. On the other hand, if you're given a speed record, you want to find the distance traveled. Now, let me draw you a version that's very simple and unrealistic. Okay. This is your distance graph. And this is your speed graph. Why is it unrealistic? Well, because in order to keep piling on the mile at a constant rate, you have to have constant speed. Okay. Now, a car has to accelerate from 0. But let's say I'm just looking at a portion of of your travel. So this is like a steady state portion. This is a snapshot of your highway travel. So from somewhere in the middle of your trip, you're traveling at a constant speed, and so your distance goes up in a line. In this case, you don't need calculus. You don't need calculus, right? So you can find the speed. How do you get the speed? You get this. You get the speed. Conversely, how do you find the distance if you're given the speed? Well, actually, the distance is equal to speed times time, right? So you find the area underneath. So here you have a line, you find the slope. You get to speed. Conversely, if you have the speed, you want to get back to distance, you find the area under the speed. You get the distance. This thing is called differential calculus, because you're studying the calculus of difference, small difference. Okay, the smaller the difference, the better. This here, you're kind of integrating the area. Okay, so it's an area you travel here plus the area here, so you're adding together. An English word for adding sometimes is called integrating. So this is called integral calculus. Right? That's it. Now, let me show you a special case of a differential calculus. Remember this? Except I don't have any general function. I have, what's the function that we did before? To the power 2, right? Two, correct? Right? So calculate this. Yeah, this is equal to this. Why do you think that is? Why do you think that is? Well, let's work it out. Let's work it out. Let's expand this. Wait a minute. You have seen this before, right? This is front, 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 back, back, front, and back, back, right? So this is a binomial term, correct? Right? This is a binomial term. So that's why when you subtract minus x, okay, and then this. This is what happened. Okay. Now, before the limit, forget the limit. Okay. Forget the limit. Well, put down the limit. So let's do this a step at a time. And this is a trick. This is a trick. The limit is to make this thing go to 0, but the top also goes to 0. So let's work this out. So I expand this and I get that. Okay. So from that, what do I get? Minus x goes away. Minus, right? Because x squared and x squared cancel out. What happened here? I take this out 1, take this out, and this becomes this. Now, because that thing that you want to make go to 0 is at the top, but not in the bottom. Now you just have this. So you just make it go away. It's very easy to make it go away to 0. And you get 2x. 2x. Okay. So the slope of x squared will always be equal to 2x. And that's why you saw this earlier. Now let's try something else. Let's try 3. Let's try 3. Now, obviously, I have to expand this, right? So let's expand this. Okay. Again, this is a binomial thing that we saw earlier, right? Front, front, front. Front, front, back. Front, back, back. Back, back, back. Right? That's how you expand. So let's put in here. So this thing now, this and that. Okay. So what's that equal to? Well, minus x squared, x cubed goes away. X cubed goes away. Take this. Take away. Take away. Make this down to 1. And this is 2, right? Now, because this thing that I want to make go to 0 does not appear at the bottom, I can make it go away. So I always get this. Okay. So if okay, so the slope of x 2, okay, is equal to 2x. Slope of x 3 is equal to 3x squared. Now, how about 4? Once again, I do the expansion. Right? Same thing, right? This thing goes away. This thing goes away. This thing cancel out. Cancel out. Okay, this will go down 1 power. Doesn't matter. All this I will get rid of anyway. So now I have this. Slope of anybody notice the pattern? Slope of x n is always n of x to the n minus 1. Okay, now saying slope, okay, saying the slope for differential calculus is not very technical. The proper word for this thing is called, anybody? derivative of this. Okay. That's it. That's differential calculus. But this is only differential calculus for a particular form of function. Now, I can give you any kind of function. Okay, and the whole thing this is a funny function, right? Okay, it's all kind of function. Okay. Okay. All kind of function. I don't know. Okay, okay. I can make any kind of function. The point is the slope will be harder to find. Okay, that is called the derivative. Now, in Mathematica, it's very clever. This is something that Python cannot do. It's called analytical mathematics. Take the derivative. It's actually the formula. This is actually the formula. Okay, it's very complicated. You don't have to do it yourself, but you can do the intuition. Okay, and if you plot this function, you see that it's a slope. So I plot this thing alongside its slope. Let's see what happens. I don't even know what it looks like. This is completely random function. I'm just making it up. Okay. This is the function. This is the slope. You notice the slope goes up, stop increasing about here, start decreasing, but still positive. At this point, the slope is 0. Now, if this were an optimization function, where would you go? This is your decision variable. This is the point of your happiness. What you would do is this. You would take the derivative of this and set it equal to 0. And honest to God, this is how you find optimal solution. So this brings you back all the way to the application. Again, in real life, okay, you will run into a situation where problem is not feasible. You have to engineer your way around it. You have to innovate your way around it. So that's one type of situation. The most common type of situation is you have multiple or infinitely many solutions. You're trying to find the one that's best. Let's say this is infinitely many solutions, and the best is here. But this is all abstract. This is like something in mathematics. You can't visualize, you can't draw. How would you do it? Mechanically, you would use calculus to find the slope and the point where the slope is equal to 0, provided that you are doing this maximization. Okay, it's the best point. This is it. This is your best point. Okay? So this is how you would do most of your problem in life. Now, I just made this random function up. You know, it doesn't mean anything to me. Okay, but that's my solution. That's my solution. So this is called differential calculus. Now, the inverse, like I told you, the inverse is called integral calculus. Okay. So those are the two things. Now, the last thing I want to show you, okay, and we will be done for today. Okay, the last thing I want to show you is why is the derivative of xn is n squared? Well, it's because you always have this binomial expansion, right? And you remember the Pascal triangle? Right? Remember the Pascal triangle we did last time? Where's that picture? Where's the picture? Pascal triangle. I have it in my notebook. If I'm not mistaken. Where is that? Anyway, I can't find it now. Okay, let's go to internet. It's easy. Okay. Pascal triangle. Right? You get this number. Okay. You get this. Now, notice this. Whenever I want to find the slope of what? X to the power n. Say x to the power 5. I would have this, right? So if I'm going to find the slope of x to the power 4, okay, I would move x by a hair, raise it to the power 4. But every time I raise it to the power 4, I'm going to have this coefficient. Okay, 1, 2, 3, 4. It's going to be x4 plus 4x3 delta and delta plus 6x to the power 2 delta to the power 2 plus 4 delta to the power 3 x plus delta to the power 4, right? Because when I do the expansion of the binomial, now, so if I do it for the x fourth, I will always get 4. If I do it for x fifth, I would get 5. So for whatever steps I take, n step, the first coefficient, the next to the first one will always be n, right? And, right, the dimension would go down. So that's why you will get this. The reason derivative of x to the power n, okay, is equal to this is because it requires you to do this kind of expansion. And this kind of expansion will always have x to the power n. Okay, you will always have x to the power n, x to the power, you always have x to the power n, okay, plus n times x to the power n minus 1 times delta plus dot, 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 dot. Okay, and then you want to subtract xn, right? Subtract xn, and the whole thing, okay, the whole thing you divide by delta. Okay, so the whole thing divide by delta. Now this will go away, this will go away. You have one delta here that cancel. Now the bottom becomes 1, this thing goes away, and everything else here has delta somewhere. Okay, so this thing can go away. That's it. That's the proof of the formula. It comes from Pascal triangle, which again was discovered, I think the earliest was in the Arab world. Okay, so that's basically the notion of limit. Now, I didn't write the word limit properly, but that's the notion. Now, the concept here, the concept of optimization here. It's very nice. It's very nice. But there is something you have to be careful of. Something you have to be careful of, which is this. Yeah. Remember I told you that in life, most of the time you will be allowed the degree of freedom. You have infinitely many solutions and you have to find the best. So your instinct should be your happiness function, your objective. What is the slope or what is the derivative of that? Set that equal to 0. That should be where you are. And there are necessary conditions to check, like, if you're at the top of the hill, not the bottom of the valley, and so forth. But let me tell you another problem. Okay, another problem. Another problem is called constraint optimization, meaning that you can do this, you will get this solution. But what if for some reason, and this I have to draw because I can't. Okay. 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 This is what you want to do, right? The slope is here. So you want to be here. But for some reason, this is illegal. In other words, there's additional condition that blocks this part of the solution, in which case it's called constraint. It's like trying to find the top of the hill, but the top of the hill is in another country. Okay, so let's say this hill that you are at is on the border of Thai and Myanmar, right? You want to go to the top of that hill. Unfortunately, as you're climbing, you run to a fence. This is called, well, I just constraint optimization. What's the word for it? So constraint. Now let me just type. So instead of having free global optimization, meaning the highest mountain you can find, you have, in this case, constraint optimization. Now, in real life, there will be other complications. For example, you can have a problem that's non-convex, and it's very complicated. So this is why you need to do further analysis, and that's where classes like mathematics, calculus, proper, and data analytics comes in. So you have some problem that's non-convex. You have something like multiple maxima. In other words, you think you're at the top of the hill, but it's just a hill. There's actually a bigger mountain. So instead of going uphill, you should have gone downhill so that you can go to another mountain, which is higher. That's possible as well. So life can get more complicated. Okay? But at the very least, right now, you have the basic element of numbers. You deal with list of numbers that represents a vector, that represents a set of attributes. And now you can deal or get to the point where you can appreciate what calculus can do for you, which is to find the rate of change, which is to find the cumulative change, which is to find the maximum point or minimum point, the point that's closest to your happiness point, okay, based on your decision. And that's going to be your problem solving. So these are all the thing that, in a way, in a very low dimensional, very low dimensional, 2-dimensional, 1-dimensional intuition. This is what you would do professionally, except in professional life, this function would be in 12th dimension. Okay, you won't be able to visualize it that easily. You might be able to do it later with this thing called dimensionality reduction, but that's not where we are here today. Okay, so I think that's sort of like what I wanted to do today. So let's check on time. Where are we? How are we doing in time? So don't save. Okay. How are we doing on time, Cup? Oops, sorry, it's time. How are we doing on time? TA. Hello. Hello.
สวัสดีครับ
ผมไม่ยัง How are we doing on time? Sorry, I'm trying to close the screen. F12 or what?
ตอนนี้
Okay, so it's a little bit over noon. So sorry, ran a little bit late. Okay, so that's it. So I think that's all I wanted to do today. Give you a glimpse of where we want to be, and this is where calculus will definitely enable you to do a lot of things. Now, obviously, calculus, you're not just trying to find the rate of change of vehicle and the cumulative distance. This function can be profit function. This function can be something that has to do with the amount of whatever number of sales or whatever it is. So it could be something that has business implication and you want to maximize that. So in real life, again, it's rare that you will have capacity for exactly 50 cup of coffee and you can sell and there are actually 50 customers. Okay, in real life you have something where it's a balance. If you make too many cups of coffee, okay, the more you make, okay, it's gonna cost you more to make per cup at some point. So there's economy of scale, there's diseconomy of scale. Likewise, your customer, okay, maybe the first cups are easy, first 100 cups can be easily sold, but the second 100 cups are not so easily sold. So exactly how many cups to produce now, it's not fixed. It's not like 50 cups. It's not like 50 customer and you only have enough coffee for 50 customer. That's it. That's the end of story. Now there's a variability, and that's the decision that you have to make. You have to choose how many cups to make to maximize some number. Usually that number is a margin, revenue minus cost. Okay, and you would do it if you have your friends in economic class. Okay, you would say that the decision making is done at what's called marginal decision making. So you make as many to maximize up to the point where your marginal revenue equal to marginal cost. Well, the only way you can calculate marginal revenue is to be able to calculate how much more money you can make for an extra cup of coffee. So this is exactly where calculus comes in, because that function is revenue function, right? Now the cup is not continuous. You can only make one cup. You cannot make half a cup. But you can imagine that this is exactly what economists mean by marginal analysis. Marginal analysis in economics relies precisely on differential calculus. The word marginal in economics is the same word as differential in calculus, roughly speaking. Okay, so that's why you cannot do economic decision making, business optimization without calculus, without, in particular in this case, differential calculus. So, and with that, I think okay, we ran a little bit over time, so let's stop with that. We'll come back on Friday. We'll have the TA show a little bit of Mathematica demonstration that they came up with, and so we conclude with what exactly we have learned and the perspective. Okay, mechanically, don't worry about being able to do or not being able to do the steps that I show you, because that's the job of your whole semester of mathematics, year one mathematics. That's what the year one mathematics for. This is to give you a perspective on why it is you are going to be studying linear algebra, why it is you're going to be studying calculus, and the basic intuition in a very low dimensional way. So I gave you a very low dimensional intuition to the problem that you would be able to do for real later in your first year, second year, and so forth. Okay, so with that, we can stop the recording. Oh, this is a last thing I did. This was just to show that matrix algebra is precisely how financial investment calculation are made, but we don't have time for that, so we'll skip that. Okay, we can talk about this on Friday if you like.